Good morning, everyone. So first, I want to ask you if have you probably checked? I have published already exercise set number 2, and yesterday you had your first session. So I just wanted to ask you if do you have any questions so far about the exercise set? I think Amelie, that's your name. Yeah, you had some corrections yesterday that we are going to fix right away. Uh, I think there was a typo someplace here, but I cannot see it now. Yeah, so I think the right value here, it's this one. It's 2 point something. 2 point. Do you have the number? No? Okay. Yeah, so that number is wrong and we have to change it. And I think that was. So there was some confusion on the. Okay, plot the wave energy spectrum. Because I told you when you apply this fast Fourier transform, what you get is something called a spectral power that is not exactly. Let's go back a bit just to refresh your and my memory. It's not here. Okay. If you remember, we have a very complicated signal, and then we say the signal can be represented as a sum of sine of different frequencies, and with each one has a representative amplitude. Okay, but I told you when you apply fast Fourier transform, that's going to give you the main frequencies that the signal is made of, but also it will give you the spectral energy. That is not proportional, but it represents in a way the amplitude. And I told you if you want to convert from amplitude to this spectral power, you have this formula, discretize. Yes? But really, just this procedure that we mentioned here of Professor Klingenberg that I told you on the exercise, that's giving you right away this amplitude. Okay? So what I'm asking you is to plot actually the amplitude versus the frequency. So don't be confused by that. So plot the wave. We're not going to call it energy, but just the wave spectrum. Okay, and that will be amplitude in meters versus frequency. And after that, you will find, when you do that, you will find something like this. Those of you who have done it, okay, you will find some main frequencies, a few frequencies that have the highest amplitude. So I want you to report those two numbers, the y and the x. Okay, one will be the elevation that we use that strange letter, and the frequency that we used f. Okay, but really we don't work usually with frequency, but we work with period. So we have to say the period one is the inverse of the frequency. Yeah, and that's the value that you're going to report on the table. That clear? Yeah. So I just fixed that, I think. plot the wave spectrum, amplitude in meters versus frequency, provide the periods with the highest amplitude on the table, and report the peak spectral period. If you remember from the spectra, you will have one that has the highest. Okay, I took it away. So that will be the peak spectral period. The main energy of the signal is it comes on that frequency. Yeah, that number has to be changed. Yeah. Well, I will put it later. Okay? Yes. Any questions so far? Yeah.
In task 3.2, you say that we are supposed to plot, if you go a little bit up here, down there. Reproduce partly the plot above by plotting all points of the scatter diagram. How are we supposed to plot all points if you only know how many points you have?
Well, no, all of that points on the table. Okay. So you have to, for example, here you can choose 12.5 as period. Okay, and here you have of 0.5 meters, you will have 192 points.
Okay, but then you have 192 points just
But
above.
it's not necessary to plot all of them because they are going to fall one on top of the other. Okay, so you have to plot one.
Okay.
Yep.
Good.
Even though it says here 15,000, you don't have actually to create the 15,000 point. They're going to fall one on top of the other. Yes. Anything else? Okay, so we go for today's topic that we are going to continue on the, so some things that we're missing about flow equilibrium. Then we are going to see what happens when we have multiphase flow. The comment about IPR that I was promising you for some time. And then some comments about the material balance and the potential, okay, the production potential. So if you, let's make just a drawing of our system. Not sure why it comes all the time. Okay, so we said last class that you can choose really any point of the system, any point of interest, and then you can plot on that particular point that's its standard conditions rate. And you can plot at that point the available pressure curve, calculated co-current. We calculated from the fixed node, pressure node, which is the reservoir pressure, all the way to here. And that's going to give you a curve that looks like that. That's the available pressure curve. And the required is calculated from the other point where I have a fixed pressure all the way back, and it should look something like that, the required. And I told you really it's very simple. The point is exactly in the same position, some millimeters to the right, some millimeters to the left, but really the rate, so there has to be one unique equilibrium rate. And that happens when I have the intersection of these two curves. That was clear so far. And I told you if, for example, I do that analysis and I make it, for example, here, let's say we put a choke and we do it exactly just before the choke and just after the choke. Then you can calculate if I want to have certain rate, a particular rate, then I can calculate exactly how much I need to choke. what has to be the delta P of the choke. Now, just to call your attention, we can do that in that way. Okay, so we have two. So let's say when we have, I will call them adjustable elements. Okay. Okay, that means when I have a choke, okay, that I can adjust. Remember that we also have fixed chokes, okay, that they don't change. And adjust, so just to make a short comment, a fixed choke is something that we call also bean choke, and it's just a restriction. It's just a piece of metal of a smaller diameter, okay, but you cannot regulate the opening. While an adjustable choke, okay, and I'm going to put here like a needle choke but is no longer in use. Okay, so you can use a cage, you can use different types, and you can regulate pulling up and down the stem the amount of opening. So that's adjustable and that's fixed. Or you might also have a pump. Okay, the pump, usually the frequency, the rotational speed of the pump can be changed. The rotational speed of the impeller, the pump has an impeller, a component that rotates, and we can change the rotational speed with a motor, an electrical motor. If we have, for example, gas lift, the gas lift injection rate can be changed. Okay. So when we have what I call those adjustable elements, you have two ways of calculation. There are two ways to calculate. To calculate what? To calculate equilibrium. One is removing that component, okay, just taking out of the system and putting the equilibrium point exactly where that component was located. Okay? And usually we call, so if that's our component, our pump, our gas lift point, our choke, so we're going to say that will be upstream the component and downstream the component, and you're going to calculate the available pressure all the way to that upstream point and the required pressure all the way to that downstream point. That clear? So this mode is useful for, this mode of calculating is useful for design. Okay. Sometimes actually we don't have the pump, but we want to know how much we will be able to gain if we put a pump on the system. Or we can replace the choke for a different size, a different capacity, and we want to see what will be the effect, what rates we will be able to achieve with that particular choke. So it's useful for design when I don't have or I'm planning to replace a component. Or replaced, okay? And also, when I don't have a particular model or a particular, when I don't have exactly how that component is going to behave, when I don't have the particular model of that component. Okay, when the numerical model is not available. And this is, or is very, it's very uncertain also. For example, you have to make some movement. Yeah, okay. For example, for multiphase boosters, for multiphase choke through multiphase flow through chokes, for example, multiphase boosters. Okay, multiphase chokes. The models that I have, usually they are not very accurate. Okay, the models can have a deviation of 50%, of 30%, and they are really, really complex. It's very uncertain and complex. So in those occasions, I'm just trying to evaluate what will be the gain of having, for example, a multiphase booster. We can use this simplified analysis. Okay, we can just remove the component and see the rate that we want and what delta P we need to breach it. Okay. And if you see, really removing the component exactly at that location, yeah, and another thing is that the desired rate and delta P have to be checked against the model once you have it. Okay, if you say to the manufacturer, I want to have exactly that delta P, a pump that gives me this delta P together with that rate, then you have to go and verify if the model provided can give you exactly that combination that you want. Okay, so you have to have some verification of the equipment afterwards. Okay. For example, let's say that we are analyzing a ESP. Okay, an ESP is something that we put very close, a pump that we put very close to the formation to lift up. So we choose the equilibrium point before that location and after that location. Okay, and we obtain these two curves. And now let's say I say, okay, I want to produce that particular rate, and I need a pump that will give me this delta P of the pump. But it turns out that the power that I need to pump that fluid is, let's say, ESP pumps, they have a range of power something between 300 horsepower and all the way to, I think it's like 2000 horsepower. Yeah. So if you obtain, for example, a power that is 3000, is not feasible. I will never find a pump that will be able to lift that rate, to provide that combination of rate and delta P. Okay? Or if you are within the range, let's say you have 700, you have to find the right model that provides you exactly that combination of pressure and of delta P and rate. That clear? So that's ESP design. And don't worry, we are going to have an example later, but just to show you that there are two ways. One of them, I remove the equipment, and then the other way is that I include, if I have already an existing component, that I know its equation, I know how to model it. The second option is including the component in the available or required pressure curves. Okay. Let's say for our particular case, let's again draw the well. Okay, let's say that you have the choke here. So that will be, that point will be my available, and that point from there on all the way to the separator, that will be the required. And in that case the pressure should be the same. So if I plot my curve, if the choke is fully open, I should have just the same curve that I had before. So that will be P downstream the choke, and the required curve that goes like that. So that's my equilibrium point, right? That curve is fully open choke. What happens when I start choking? When I say, let's say I had 100% opening, now I close to 80%. What curve is going to change? The available or the required? The available, right? Because that's the available curve is including the choke. That curve includes the inflow, okay, the IPR, includes the tubing, and includes the choke. And that includes just the separator and the pipeline. Yes? So that's the curve. The available curve is the one that should change. And how should it change? So you think when you choke, the rate should be reduced, right? The equilibrium rate should be reduced. So the curve does something like that. Okay, and the rate is reduced, and that will be, for example, with 80% opening choke. When you start closing, you have 60%, 50%, etc. Okay, that clear? And all of them, of course, if I have no flow, I reach the same pressure because I have no flow, right? So the same pressure when rate is 0 is the same point. But you see two different philosophies. One of them, I take away the component, I say what is the delta P that I have to breach, and the other, I include the component, but then I have to calculate for different values of that component, for different settings of that component. Yep. So that's done for if I have already, if a particular model it's available, I know exactly what pump do I have, and what pump do I have, what are the characteristics of that pump, what choke do I have, and an equation is also available. And the equations usually, just to give you some idea, for a ESP, for a pump, looks something like that. Delta P equal to a coefficient A, that is a function of the frequency times Q squared plus B, and this is the actual rate, okay? Plus C has a function of the frequency, and for a choke, something like that. It's a coefficient called, let's call it D, times Q squared actual. So I include just that equation. For example, I come with certain, I fix the rate, calculate the IPR, calculate pressure loss in the tubing, and then I come to that equation. I use the rate that I have, the frequency that I have, and then I calculate how much the pump is going to increase, and that's how I find one point in the curve or choke. Okay, what pressure is just pay attention that all of that is in actual rates. Okay, actual rates is local rates, local volume rates at P and T, and usually these are at the inlet of the component. And remember that everything, for example, we had flow in the formation, that's based on velocity, right? Darcy law is based on local velocity, that you need local rates, right? We will see flow of gas in the tubing also depends on local rates. And multiphase flow also depends on local rates. So every physical principle of pressure loss in every part of the system is based on local rates. What we need to put later is that conversion parameter from standard conditions to local rates. Okay, just keep that in mind for the future. And this is this operating mode number 2, including the component, is the operating mode of most of the commercial software that you will use in your career. Okay, for example, PipeSim. So let's put it here. Commercial software. Use this mode. Okay, and that we have PipeSim, for example. We have Gap. We have Prosper. We have some other tools by, it's called Rio, I think. That's by Weatherford. We have Pipephase. Okay. And all of them use that technique. But I'm going to tell you just now just a question. So first, one main disadvantage is you need to have the model. Okay, you need to assume a model or find a model. So you need to do a pre-design. And for field development, that's really not so comfortable, because initially you just want to know if a pump, for example, will be able to help you, right? But you don't have the specific model of the pump. So this procedure in a way forces you to choose one particular pump model from the catalog. Yeah? Then the second issue is, I'm going to ask you, what happens if I say I want one specific rate? Okay? Let's say I want to see if one specific rate is feasible or not. What will be the procedure if I do it using this mode? I just come, plot my two curves, excluding the component, yeah, and then I put my rate that I want, and I see, okay, it's feasible. Okay, it's infeasible. That's it. Okay, and I know if I can produce it or not. Now I'm going to ask you, what do I have to make with this particular, if I have a rate here? Okay, I have some convergence process where I have to find exactly the opening to give me that particular rate until these two lines cross. Yeah? And convergence process is iterative process, and iterative process takes time. So usually this process, and people call it, for example, solving for a desired rate. Okay, and I'm adding also, so if you see here, for example, in the case of the choke, this D loss coefficient will depend on the opening of the choke. Okay, so I have to assume first, for example, fully open. I try to find the crossing, and then let's say it gave me too far to the right, too high. Okay, then I use another procedure, then I use another opening, I find it, now it's too low. So I have an iterative process to solve, to change that D, that coefficient, until I have exactly the intersection that I want. Okay? And what is the problem of those equations? Well, here I very simplified, but really they are a bit more complex. Okay? Let me show you, for example, for gas, I think I have. Okay, that's how the pressure loss looks like in a choke for a gas, for dry gas. Okay, and this A2 is the opening of the choke. And that can go from fully open, that will be the area of the pipe, to fully closed, that will be 0. Okay, but in that case, I have to assume an opening Okay, then calculate the delta P and then calculate that curve. Okay, the intersection will be here. That's not the rate that I want. Now I change again the area. I obtain another rate. Yeah, that's close, but not exactly close. Now I change again the area, find again a new intersection, and so forth. So to have that equation there in the solving process, it's making it heavy and making it that you need an iterative process. So, for example, for a dry gas well with a choke, first assume an opening. Calculate the intersection. Okay, Q, for example, star. Check if Q star is equal to the Q that I desire. Okay, if yes, finish. Okay, and I have exactly the opening that I want. If not, I have to assume another opening, calculate intersection, check, etc. And in this process, I use any method. I can use Newton method. Okay, I can use any method. And don't be confused. That sometimes, and we will see in GAP, for example, is called optimization. Okay, so that's wrongly called optimization. Okay, optimization we will see later. We will have a week to talk about optimization. But basically, you also have a solving algorithm based on Newton. But in that case, I want to maximize, for example, oil production by changing some variables that are in the production system. But sometimes, don't be confused, so some commercial software use the word optimization. So you say you're performing an optimization to find the rate. And that's not really optimization, you're just solving. Okay, solving an exact opening for finding the rate that you want to produce. But so the negative points is the component model is usually highly non-linear. Chokes, pumps is highly non-linear, so that's bad for the solver. Okay, remember, if we add more non-linear equations to that Newton-Raphson, it becomes very heavy. Estimate the derivatives, you have all of these square roots, you have all of these ugly things that if you assume a wrong value, it might diverge or it might not converge. Okay, and takes more time to evaluate. Okay, while for the first option we really just have to take it away, find the available and the required, and see if the available is higher than the required. Period. Doesn't matter how you're going to do it, but you will see, you will have a physical solution, you will have a component that will bridge that difference. Yep. But hopefully we will have a session on gap soon, and we will revisit that that issue. Okay, so now another comment that I want to make is that the equilibrium rate can be affected by, I can affect somehow the inflow and the outflow, the available and the required, right? The operator or the engineer can affect the available and required pressure curves. For example, let's say that you have that particular system, okay, and you have that rate, and you say, I want to try to see now if I get a higher rate by modifying the inflow? What can I do in that case? Let's say that this includes the IPR and this includes the tubing. Okay, tubing plus pipeline plus separator. Okay. And that's PWF and Q. So what can I do so the inflow will be bigger? Okay, because if I want to make the intersection higher, the rate higher, I have to make it, scale it and make it bigger. So what techniques do I have for an existing system, an existing well, just to increase its productivity? That brings some memories. You have some stimulation, right? Acidizing, fracturing, stimulation, acidizing, fracturing. Okay, and it's things that you see if the PI you have, let's say if it's a linear or if it's a, let's put it, you know, squared, like for the gas back pressure equation. So you're trying to change that C and just increase it a little bit. You won't be able to make a very dramatic increase because you are bound to that point. That point, it comes given by the reservoir pressure. But you're able to increase a bit the productivity by some of these techniques. Okay? Some other more dramatic changes are, for example, to make to close the branch and to make a sidetrack and make a longer wellbore. In that case, you can change completely the characteristics of the wellbore. Okay. Now, what changed? So that's one way to do it: changing, modifying the inflow. Okay. So how can I change? Make the same change, bring the outflow. How can I modify the intersection, making changes in the outflow? Any ideas? Yeah, and this is a true story. Okay, it's like you are going to graduate. I'm not sure next year, right? And you're going to get to your well, and then the first question they're going to ask you is, how do I increase productivity of my well? And you're going to say, oh yeah, I have an easy solution, put a pump. And they're going to say, no, but you have no budget for, or limited budget for that. Okay, and you will have to start finding ways to change the intersection point, low cost measures. Yeah. So one way is to stimulation, acidizing, fracturing, and how do you change the TPR? Okay, the tubing curve. Yeah. Okay, we say no pump. We don't want to change the system, just the way it is. Okay. What happens if I manage to reduce the wellhead pressure or the separator pressure? If I reduce it, I should get more rate, right? So the curve does something like that. Okay. So let's say that's just tubing, okay, plus wellhead pressure. Okay, so that's for P wellhead 1, P wellhead 2, P wellhead 3, and 1 is higher than 2 is higher than 3. So by reducing the wellhead pressure, I can increase the production rate. What else can I make? I can increase the diameter of the tubing, right? If I make the tubing bigger. Okay, that will be tubing 1, 2, and 3, and 3 is bigger than 2, bigger than 1, and that's tubing diameter. Okay, changing the tubing is a big operation, but can be done if you justify how much more extra you're going to gain by changing the tubing. Okay, another thing might be that the tubing in that condition you checked and there is some scale on the tubing. Okay, scale is like inorganic salt that deposits in the walls and comes from water, okay, from all of these minerals in the water, and is with time accumulating and making the flow area smaller and smaller and smaller. So what you can suggest to your boss is say, okay, I will come with a tool, with a reamer that will take away all the scale in the walls and then increase the size of the tubing, increase the diameter of the tubing. Yep. So we always can influence these two curves in one way or another, okay? But if you want to make low cost improvements, you are limited in how much you can gain. Yep. Another thing that you can use these two curves is, for example, you plot them in the software, okay? You take, okay, I know exactly that's my inflow, I have some well test information, I have the correct IPR, I have all the geometry of the well, and I put that and I say, okay, I should be getting from that well, for example, 2000 standard cubic meter per day. And when I go to the field, I see and I measure, and actually I have 1000 standard cubic meter per day. That means that I have much more pressure drop in one of the two curves what I should, right? And then I have to find where the problem is with pressure measurement. Okay, I have to find if it's a problem located in the tubing, is it because I have an obstruction, if it's because I have scale, if it's because I have some corrosion, or is it a problem of the formation? I have, for example, the sand collapse. Okay, I have too much restriction to the wellbore. So I can use that for diagnostic. So just keep that in mind. Equilibrium analysis. Okay, for diagnosis. I see what should be the theoretical intersection, and when that intersection is very far away from what I'm actually producing, there is something wrong in my system. Okay, and then I have to find what is wrong. Okay, we take a break, yeah, 15 minutes. So that was just to tell you, you know, there are two ways. One of them, we have the two curves, exclude the component. And something very, very important is that we have to verify if that combination of rate and delta P can be produced by the equipment. That has to be done. We cannot just rely, okay, we will find a pump, ideal pump, that will have, for example, 4,000 horsepower, and that will be able to pump that rate. You have to verify. Sometimes also that equipment is very, very expensive. So it's more, is within your budget to choose a smaller rate, okay, a smaller pump. And the other way is to include the model. It's more time consuming, requires an iterative process, and people wrongly call that optimization. And it's a non-linear model, it adds complexity, and you need to have a model. Okay, so you need to define some booster that you're going to use in the software. just to mention that why we want a particular rate, you're going to say the system produces what the system wants to produce, right? We are bound by the system. We are not bound by the rate. The problem is that in all of this design process, I told you that reservoir engineers, they calculate some rates, right? So the logic is more or less, okay, during the field, okay, so first, reservoir engineers use reservoir simulator with, remember, this minimum bottom hole pressure, flowing bottom hole pressure, and a target rate. and they repeat that process, those simulations, or they perform many simulations to find optimum, for example, number of wells, to find the recovery factor, to find a configuration that gives them maximum NPV, etc. Okay, and after they say the rates that we want, so we have for each well Q oil desired, okay, versus time, how much I want to produce from each well in time. Then I come back and I talk to the production engineer. Is that rate feasible? Okay. Then I come and I ask if that minimum bottom hole pressure that I put, if I can produce it at that particular point in time. And the production engineer has to verify if that rate, if I can make that rate. Okay. And here comes some back and forth between reservoir and production engineer. Okay, comes some communication back and forth. The production engineer might say yes, but you have to install a big pump, and then the economics say no, that will be too expensive. So the production engineers say no, then you have to use a lower rate and use this minimum pressure, and then the reservoir engineer goes back, does their calculation, they come back, now are these rates okay? Production engineers check again, yes, now those rates are fine, but you could produce a bit more. So we have that communication at a later stage in the design process. Okay, after that's when I have my system defined, when the production layout is defined. Okay, but many people wonder why, because at this point, for example, the reservoir engineers say we're going to get certain recovery factor, certain production, and then when they come to that part, when the production engineer is verifying the rates, it might be that you're not able to produce those rates. And people ask, so why there was such a big difference? The big difference is because reservoir engineers are neglecting an important part of the system. Okay? But that's part of the game. So keep that in mind, and we have two modes: neglecting most of the system, and then including the system and use it for verification purposes. We compute, so we say here we compute, we'll define for each well Q versus time, how much I want to produce. And the task of the production engineer is really to honor that rate. It's like, I will try it because that's the rate that you found that is the optimal rate. It's really the rate that is the best for that reservoir. So the production engineer will try to honor that rate at all cost, okay? By using equipment, by making changes, by maybe changing the layout, etc., okay, on the design process. But if it might be a point that you cannot produce that rate, the rate is not feasible, then you have to go back and include that maybe with a higher back pressure on the sand face, or maybe changing the rate, or the rate is feasible. And you might ask, you say, so it's kind of strange, so why you don't use, if that's going to be a big problem later, why people don't use the two models at the same time, right? Maybe some of you have that question. Why not to use the two models from the beginning to make your calculations? There are two main things. One of them, with the system, the production layout is defined at a very late stage in the design process. Okay, so you just have the reservoir model. Okay, and then the next thing is that to put these two together to reservoir simulator, plus the production simulator, that's called coupling, okay, of models. And that coupling is kind of something that has been emerging in the last years, and it's not really yet fully adopted by companies, okay, to work with the coupled models. They prefer to work on two separate departments that have some communication in certain points in time. But really, ideally, will be to work with one coupled model that takes the two things into account to avoid so much back and forth, okay, to make a more efficient transfer of information. So keep that in the back of your head. So why we want to honor a rate, if really the rate is defined by the system, right? It's defined by equilibrium. We all, as production engineers, try to honor the rates that given by God. In this case, God is the reservoir engineer, that he knows what's best for the field, what's best for the reservoir, and we try to honor what this guy said. When we cannot honor, we say, no, sorry, this value of rate that you provided doesn't work. Please try with something else. And sometimes they get stressed because they want to get, if we don't produce exactly that rate, we won't achieve the required recovery factor or the required drainage from certain region. Okay, so that's sometimes a bit stressing situation. Now I want to make a comment on what happens when we have multiphase flow. Okay, multiphase flow, it means simultaneous flow of gas, oil, and water in parts of the production system. Okay, I told you already that for the IPR, for the flow through the formation, the IPR of oil, for example, if we are flowing in saturation, is going to look curved, okay? Something like that. And we are going to discuss slightly more on that later. But that's the oil, and the gas, you just multiply Q of the oil times GOR, okay? And the Q of the water, we just multiply Q of the liquid times water cut. Yep. So here we have one equation more to make. Q of the liquid is Q of the oil plus Q of the water times water cut. And then you have okay, I think it's like that. But that's how you clear, if you have just the rate of oil and you have the water cut, that's how you calculate the rate of the water. Yeah? Is that correct or not? I hope so. 1 minus water cut. Yeah. And water cut here is a fraction. Okay, that goes between 0 and 1. So that's no problem for the IPR, and we already know how to handle it. But what happens with the TPR, the flow in conduits? Okay, with the flow in the pipeline, with the flow in the tubing, with the flow in all of those parts. So I'm going to tell you now just a secret, okay? And separately, we will try to make a short discussion on multiphase flow. But I'm going to plot now the required pressure at the downhole, okay, for multiphase flow. And let's make our system Let's make a picture of our system, and we have to make it a bit bigger. So let's assume that there is some fluid entering into the formation, and that fluid has a composition set I. Okay, by composition I'm referring to, for example, methane, CH4, and has certain volume fraction, mole fraction. Okay, set 1, and for example, we have also ethane, C2H6. C3, propane, C8, etc. Okay, we have a bunch of components, and we have the composition, the mole fraction associated to each one of these components. Yeah. Now with that composition, we can create a phase diagram. If you remember T and P, pressure and temperature, from your studies in the kindergarten. Okay, let me make it a bit bigger. Okay, and that tells you that part more or less is gas, that part is in liquid, and this part you are in a mixture. Okay, and actually you have some lines that they do something like this. Okay, that they define how much vapor you have in the that will be mass of gas divided by the total mass. Okay, this X, what I call the quality line. So here the quality is what is equal to 1, so that's the dew point line. That's when at that particular combination of pressure and temperature, I have exactly just the first mist of liquid condensing from the gas. In this line is the bubble point line. That's where if I have a liquid, when I reach that particular pressure and temperature, I have just the first mini droplet of gas coming out, bubble of gas coming out of the oil. Okay. Now let's assume that that point is someplace here, okay, inside, that I'm entering already in a mixture. Let's put it on that side. We are saying it's an oil. Okay, so we have that point. And when I'm going evolving in the tubing along the system, I will be losing pressure and losing temperature, right? The fluid will be being cooled, and also the pressure will reduce. So the line will be something like that. That means that I'm increasing. At this point I have certain mixture, okay? And then when I'm progressing along the tubing, I'm increasing the amount of gas gradually. So let's say here, initially we can say, for example, that we have just a few bubbles of liquid. Then, for example, the bubbles start to coalesce and they make a bigger lumps. Okay. Then again, they coalesce a bit more and they form some kind of a very nice shape called Taylor bubble. Sorry. And maybe even at the end of the tubing, I will have just oil on the walls and then a big amount of gas. Okay? And here I will have something similar. Yes? So that's what we call, here we have simultaneous flow of oil, gas, and water. in the tubing. And that's what we call multiphase flow. And I can have these different configurations of the fluid inside the tubing. That's what I call flow pattern. That's configurations. This is what I call flow pattern. Okay. When it looks like that, it's called bubble flow. When it looks like that, it's called churn flow. When it's looked like that, it's called slug flow. And when it's called like that, it's called annular flow. Annular. Then we have slug flow. Then that's called churn flow. And that's called bubble flow. Now all of that is to just to go back to that figure. So how it's going to look like for multiphase flow? It's going to look surprisingly something like that. Okay? When you have one phase, either liquid or gas, it's going to look all the time like that. Okay? No matter what. All the time monotonous increasing. When you have multiphase flow, might or might not, but usually it looks like that. You have one part that is descending and one part that is ascending. So that will be PWF versus Q. And that PWF, remember that PWF, we are looking at, for example, if we make it at a fixed wellhead pressure, we're going all the way down here. Okay, that's the required pressure curve. So why that happens? Anybody knows? There is a specialized course on multiphase flow taught at the energy department by a professor called Ole Jørgen Nidal. That if any of you is interested in more multiphase flow, you can take it. But the main reason is that okay, let's try to make a simple explanation. When the rate is very, very low, okay, let's see the cross-section area of the pipe. Okay, that's my pipe. When let's put, so when the rate is very, very low, the liquid, the two phases go usually at different speeds. Okay, so that's something that you have to understand first. Okay, the liquid, the gas, and the oil, they don't move at the same speed. Okay, they don't move like a unit. They move at different speeds in the tubing. Okay, but when we are at very, very low speeds, the oil moves much, much slower than the gas. Okay, and when I start increasing the rate, the gas will move much, much quicker than the oil. Okay, yeah, that's yeah, I think I'm just trying to find the okay, so before that, okay, the pressure drop in the tubing, okay, depends on two components. Okay, just like multi-phase flow or single phase flow, it depends on two components: delta P hydrostatic, okay, plus delta P friction. Yep. Okay, when I'm in this part of the curve to the right, the frictional pressure drop is going to dominate. Okay, that's a function of rate. And in that part of the curve, that part of the equation is much higher than this part. Okay, so that's why it's going up all the time. Yes? Now, when you are on this side of the equation, then that part depends on how the average density of the mixture in the tubing, right? Yes? Remember that this, if we make it for single phase flow, is rho m times the height times the gravitational acceleration. Yep. And this rho of the mixture depends on how the phases are distributed in the piece of pipe. Yes? Okay. So what I'm saying here is that when I'm increasing the speed, the gas first in this part of the area, the gas doesn't drag the oil. Okay, you have certain, if you put them separately, okay, if you put the oil, for example, okay, that's just the oil. We are just taking it out, okay, and you have the oil. You will have some shear stress caused by the gas. Remember, the gas is going higher, so it causes some force to pull the gas up in the interface. Okay, but at very low rates, that's not enough. That's not enough to lift it. So the oil will take a very large area, okay, because it's moving very, very slow. Okay, remember that. Remember that the velocity of the oil times the area that the oil occupies should be the rate of the oil, okay, which is constant. Okay, so I can either have a very high speed and low area, or a very high area and low speed. Okay, so what happens initially is that the gas, because it goes so quick, it doesn't manage to drag the oil. It occupies a very small area. Okay, but then as I increase the speed of the fluid, as I increase the rate, the total rate, and let me make space here, then that force, that shear force that the gas is exerting on the oil is helping it to go a bit faster. Okay, and when it goes a bit faster, then the cross-section area is going to be reduced. Okay, so now here the oil is going, the velocity of the oil is a bit higher, and the velocity of the gas is also a bit slower because the oil is slowing it down. Okay, and at the end the rho of the mixture is, how is the rho of the mixture of this case compared to that case? If you have more liquid in the tubing, the density should be similar to the liquid, right? If you have more gas in the tubing, the density should be closer to the gas. Okay, so that part, this hydrostatic pressure loss, it becomes less when you move on this direction of the curve. Yeah, so that's the reason. That part increases just because of friction. The same phenomena we saw for single phase flow. When we increase the rate, all the time you will get more and more friction. Now this part goes down because initially, when the velocities are very, very low, then the liquid occupies a very big part of the section area, okay, and the gas flows very quickly. Okay, then the density of the mixture is very high. But then as I start increasing the rate, the gas starts to make more shear on the oil, starts to lift it. That makes that the gas will go slower and the liquid will go faster. When the liquid goes faster, the cross-section area is reduced, and because of that, the density of the mixture is reduced, and because of that, the hydrostatic term is reduced. Sure. Okay, I hope you can explain it later if I ask you the question. Okay, but no big. So the curve usually goes down and then goes up. What are the consequences for our equilibrium? Okay, what are the consequences for the equilibrium point? Okay, if you now we put the inflow PWF versus Q, and we have that curve, and we have this curve. Okay, in that case, doesn't matter. Okay, we just have the equilibrium. Now, what happens if I have this case? And that ends up someplace up here. And if I have that point here. Okay, you could have, so note with multiphase flow I could have two intersections. Okay, and that's something that really, if I'm solving my system automatically, I could converge either to that condition or to that condition. So you ask me, are there really two equilibrium points in the system? And the answer is yes. The system could operate potentially at any of these 2 points. Okay, but there is, that point is what we call stable. Okay, if you're going to make an analogy, it could be a ball that is in the lower part of a valley. Okay, when we move it to the right, it's going to go back to the center. When we move it to the left, it's going to go back to the center. While this point is unstable. Okay, if I make a small perturbation to the right, it's going to fall, or if I make a small perturbation to the left, I'm going to fall. Okay, so let's see that with, for example, that point. Okay, I have this equilibrium rate. The system is operating at that equilibrium rate. Now, I did something to the system that the rate increases slightly to the right. When the rate increases slightly to the right, the required pressure is higher than the available pressure. Okay, that means that I need more pressure than what I have. That's going to cause that the point will be dragged to the left. Okay, because I don't have enough energy, so I have to reduce the rate. The same thing here. If I, for some reason, the rate fluctuates and goes to a value that is lower, in that case I have more energy than what I need. So the rate will return back to equilibrium. Okay, that's not what happens here. Here, if I make a perturbation and I move the rate someplace to the left, okay, the required pressure will be higher than the available. Yeah, and that means I reduce the rate. Reduce the rate until I reach rate 0. The well is dead, stops producing. Yeah. Now if I make the perturbation on the other side, all the time I have more energy than what I really require. So the rate will increase until I reach the other equilibrium point. Yeah? That clear? So that's the consequence for our equilibrium. So in that case, the PWF required is higher than PWF available. That means the rate is reduced. And on that side, PWF available is greater than PWF required. That means that the rate is increased. Yep. And in this point, the same applies. This applies. So the rate, I have to make a copy. bit messy. Okay, and in that side, if I make a perturbation on that side, then the required will be greater than the available, and then the rate is reduced. But I can operate, potentially I can operate on that point, okay? It's an equilibrium point. Okay? So one more thing before we abandon multiphase flow. So for multiphase flow, pressure drop calculations are time consuming, and we will see later why is that, but basically they have to be done in a discretized manner, and I have to calculate the local rates to flash. I have basically to go to this diagram for a given pressure and temperature, flash, find how much oil, how much gas we have, then I have to find this leap, this difference of velocity between the two phases, and then I have to calculate the pressure drop using some expression or correlation. So it's very time consuming. We are going to have a short session on that later, but basically it has to be done in a stepwise manner. I have to make a flash, okay? That means determining amount of oil and gas, and then I have to determine the slip between the phases, and after I do that I can calculate the delta P. That will be for one position in the tubing, and I have to make it for several positions, I plus 1, I plus 2, I plus 3, I plus 4, etc. So it's a very time consuming and computationally consuming computation. So usually what we do is that we store, to save time, the TPR is stored, is pre-computed and stored in tables beforehand. Okay, for example, we make a table, that's what we call tubing tables, or also called VLP, vertical lift performance. Sometimes they also call it tubing table, TT, vertical lift performance. There is another name. Okay, well, we pre-compute. For example, we say the table is done for a given wellhead pressure. Wellhead pressure equal to wellhead pressure 1. Okay. Then I calculate for certain rates, Q oil, Q gas, and Q water. I have some values on the table here. And I pre-compute the PWF for each one of those rates. Okay, and also the temperature. So that's equivalent, if we look at our plot, okay, that curve, I describe it by a collection of points, the PWF, and that's a PWH equal constant, equal PWH1. So I make compute for that rate 0, compute for that rate, 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 and those points are the one on the table, okay, each one of these points. that point goes here, that point goes here, okay, and so forth. That clear? So the tubing table is I pre-compute, I have a model, okay, and because it's so expensive, I don't want to run it every time I need a calculation, but I just pre-compute a table, and then we use the table later. We use the table as our multiphase proxy, okay. I don't go anymore to the equations, but I just used interpolation on the table. Perform interpolation. Okay, so for example, if you want certain rate that is in between those two, you just perform a linear interpolation to find PW, to find that point. If I want to have exactly for that particular rate, then you have to perform a linear interpolation between those two. Yep. One problem is that, so you need, so just to make some warnings, there has to be an appropriate number of points on the table such as PWF interpolated has to be as close as possible to the PWF calculated, okay, to the one that I will calculate live from the program. If I, for example, in this case, I put just one value here, one value here, and one value here, then the interpolation between these two doesn't capture the behavior in between. So tables, very nice, saves time. I just perform linear interpolation. Linear interpolation is fast and cheap. Okay, so I'm happy. But I have to put enough points to be sure to capture the real behavior. Another thing is to find the intersection. Okay, for example, I have a collection of points for the IPR. That will be something like this, and I have a collection of points for the TPR. Okay, so the intersection, let me make that ended up a bit curved, so it should be more like that. So the intersection point, I have to find it by intersecting two straight lines, and that's much more simpler and computationally inexpensive than to run a full nonlinear solver, okay, to perform a Newton-Raphson. So that's just intersection of two straight lines. Computationally cheaper than nonlinear. Okay, so there are some advantages to use tables, and actually in the old times that to run this routine was very expensive, so that's why they wanted to do it from the beginning, everything, so they don't have to worry anymore about multiphase flow, and they stored. And actually that's what we do now in Reservoir Simulator. Okay, in the Reservoir Simulator we use those tables. Something worth mentioning before we take the break, there could be with time oh, so one more thing is that in that case, if we are sure what is the wellhead pressure, okay, that we have, but really if we have, for example, a flow line, okay, if we have the system that we showed before, then the wellhead pressure won't be constant. but will also be a variable. So you usually have several tables for each wellhead pressure. For different wellhead pressures. Okay, wellhead pressure 1. You're not exactly sure what will be your wellhead pressure, but you can compute for many of them. Okay, 2, 3, 4. And then in the solving process, you have not only to interpolate, if you have, for example, a flow line, you won't have only to interpolate on the rate, but you also have to interpolate on the wellhead pressure. Okay? If you're not exactly sure which pressure is what you have. And now, with time, the well GOR changes. Okay? Water cut change. So you have to include that variation also on the table. Okay? And that comes just because you're making, taking more time. That's why but I think it's necessary that you get that part okay. For example, initially, let's say that you were producing from a reservoir that had a gas cap and had an oil layer. Okay? When you were producing initially, you initially will get only a few bubbles of gas very close to the wellbore. Okay? With time, they begin to be bigger. The areas, the saturation around the wellbore starts to get bigger and bigger, and that changes when you increase the saturation of gas. Then you increase the relative permeability of gas, and then you will get more gas flow towards the wellbore. Thus, the GOR increases. Okay? That also happens if you have coning, for example. So let's add some more. With depletion, the saturation of gas around the wellbore increases. That means that the relative permeability of gas increases around the wellbore, and it flows, more gas flows towards the wellbore. So then the GOR increases. And also the same thing if I have coning. For example, in this gas, the pressure is so low that it penetrates and enters into the wellbore, then the GOR will also change. And the same thing will happen if I have an aquifer. Okay? The aquifer might also invade into the well. So in that case, the GOR and the water cut change, and in that case, I have to make tables not only for different wellhead pressures. Let's put it here. So usually it is necessary to build tables for different GORs and water cuts. Okay? And then the table becomes really big and big. So that will be for a GOR 1, water cut 1. Then I repeat the same thing. So that will be, okay, for a fixed GOR and a water cut. Then I repeat now with another, the same for the same wellhead pressures. But now with another GOR, but the same water cut, for example, with GOR 2, GOR3, water cut 1, water cut 2, water cut 3, and if you see in this case we're changing only 3 values, and already the amount of tables that we got is huge. Okay, so that's usually what we do with tubing tables. Any question? No? We take a break, 15 minutes. Sorry, this class is many concepts, okay? We don't have too many exercises. They will come later. But I try now to cover some of the, on that part that, let's go back to, okay, on that part, this block that has a lot of very important concepts, okay, I'm going to try to cover through all of them, and then hopefully in the exercise and some sessions we will have here, you will understand. It will help to kind of solidify these concepts. Okay, so now the next thing I want to comment, okay, now we talked about tables. Multiphase flow is challenging, so we want to compute them beforehand, and sometimes we work with tables even though we have the model, okay, if we can compute it, just to save time. But be careful, the number of points is very important. Okay, so you have to run sensitivity with different number of points until you get the same, very similar to the value that if you run live the simulator. Okay, then one thing that I want to make a comment is on IPR, inflow deliverability. Okay, or what we call the inflow performance relationship. And that's for a given, if you remember, for a given time, or for a given, that means for a given reservoir pressure, and also for a given depletion state. Okay, for a given is how do we represent that formation that is very complicated, okay, and has a lot of phenomena. How do we represent it just by a simple equation called IPR, where we have the rate and the PWF, and we see what pressure do we need to deliver certain particular rate. And if you really, you ask a reservoir engineer what is IPR, they don't really use it, okay? If they want to find the rate, they just go and change the rate, and they obtain the bottom hole pressure. But for production engineers, that they do with the reservoir model, okay? For production engineers, that's extremely important, because at any point in time, you want to see what happens if you make variations in the system, okay? What will be the intersection? So reservoir engineers use reservoir simulator. Okay, but remember, it takes time, is expensive. For production calculations, is time prohibitive, okay, to use the reservoir simulator. So we want to have a curve that represents the behavior, the flow behavior of the reservoir. And that's the near wellbore formation. Okay, if we have, for example, like this vertical well, the top view, if we see it really, the region that affects the flow towards the wellbore is a radius of, let's say, 500 meter, okay, or 100 meter. And the cells in the reservoir simulator, they are usually that size or even bigger. So they are making the approximation that all the well is in one cell. Okay? And that's good for drainage strategy, for a recovery factor, for the overall field. But for production, we want to focus is just in this area, the area that is closest to the wellbore. Okay, so that's why we use IPR. Then, just to call your attention to something else, if we have the wellbore, okay, and we have the formation on that side, and let's say initially everything here on the y-axis, I'm going to put an axis here that will depict pressure, and another axis here that will depict distance, radial distance from the wellbore. Yep. So initially everything is going to be at a constant reservoir pressure. Okay, when I have the well is closed, well shut in. Now when I start producing, when I open the well to production, what's going to happen? That point here is going to go very quickly and take its PWF production rate, right? But the porous media that is exactly next to it still hasn't felt, still has some drainage, so the fluid starts to go from that point to that point, but still doesn't feel it. So at a very early time, you will have just that distribution. It's almost like a sharp peak going up and remaining constant. Okay, so that's time 0. We can start maybe using different colors. I think that will be wise. Okay, so that's time 1, time 0. Then at a later time, I'm starting to affect farther away from the formation. Okay, then so that will be time 3. Then let's use this black. Okay, and here I have no flow. Okay, that will be a no flow, and we will talk about, so what is this bound here? What is the limit? Until where do I plot it? Any ideas? It could be a fault. Okay, I have my well here and I have a fault located exactly there, so that's going to be my no flow boundary. It might be that I have just 2 wells neighboring, one next to the other, and that will be the location of the boundary, just in between them. Okay, it might be, yeah, you have a fault, you have just the end of the reservoir is there. Okay, so you have a shale layer. It might be that you have, for example, the aquifer at the periphery of the reservoir, etc. But there will come a point where, I'm not sure if I put that again. Yeah. There will come a point in time where exactly I reach the boundary. Okay, the pressure disturbance reaches the outer bound, and at that point is what we called stabilized flow. Okay, that the pressure, what we call the pressure perturbation, reaches the outer bound. And at that point is where, that's what my IPR is representing, exactly that particular pressure distribution. Okay, and also, so we say the IPR applies usually for stabilized flow, or what we call the stabilized flow, we call it also PSS, pseudo steady state. Okay? It's not really steady state. Everything is transient all the time in the reservoir. When we are draining, that's going to change with time. And what will change actually? Let's say if we now start depleting, the pressure in the reservoir will go down. Okay, so that's T4. Let's call it T5, I think actually. T5 and T4. And with time, at the later time, it will be like that. It will be like that. Okay. Problem solved. Okay, and it will remain the same shape, but it will be declining, declining, and declining. Okay, so that's where the IPR usually applies, on that point that we call stabilized flow. If you ask, okay, then what happens? Let's take that particular figure. Okay, you say, oh, but you're saying that, but it might happen that I'm producing with some PWF, and then I change that PWF to a lower value. I will have exactly the same thing. I will have first a period where I have transient, 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 until I reach and I affect the boundary, and then I will be exactly at that point at another pseudo steady state. That's where the IPR applies. The IPR doesn't try to capture these short transients. It's exactly for when I have reached stabilized flow. Yeah? And you will see if you make a multi-rate test, okay, if you lower here a gauge and you measure the pressure and you measure the rate, okay, the rate I measure at the surface with a separator, you will see that the rate change initially might decline and remains more or less constant. Okay, then if I change PWF, they will have a transient behavior and then will remain more or less constant. Okay, so these are the points that I take for the IPR. That combination of rate, that will be rate and versus time, and PWF versus time. If I change, I had here 1 PWF, I change it to, it has to be lower, okay, and I lower. So those are the couple that I will take to plot my IPR, those two. One it has stabilized. So the IPR contains information. We are, that's covered in other courses, but the IPR contains information about first about location and type of outer bound, usually the outer bound is no flow. Okay, that might be a fault, that might be a neighboring well like I explained, but also might be constant pressure. If you have, for example, one well that is producing and one well that is injecting, this well is all the time pushing some injection front, and in that case you can assume that that behaves like a constant pressure for this well, for the producer and injector. And if you are pushing and pushing and pushing, you're trying to keep the pressure constant. Yep. So that's one particular case where you might have constant pressure. And the location, how far away it is. Then another thing that the IPR contains, it's permeability of the formation. Okay, or we can say these are rock properties of the formation. It also contains information about the fluid properties and their variation with pressure. Okay, remember temperature doesn't change in the whole reservoir area. But if you remember, that has to do something with Darcy, okay, that we say the velocity it's equal to dp dr, okay, k over mu, and then we have to change that. We want all the time to have the rate in standard conditions, so we have to convert that equation, and for that we use these fluid properties. Then another thing that it takes into account is oil, gas, and water saturation in the drainage area. Okay, SO is gas and S water. Why? Because that defines the relative permeability of the oil, relative permeability of the gas, and the relative permeability of the water. How easy the phases can flow through the formation. Then another thing that the IPR captures is restricted flow towards the wellbore. Okay, for example, we have in the perforation, okay, if you remember, we make shoot like a bullet, okay, and it makes an opening, and that flow, that is going to affect the flow towards the wellbore. So that part is also captured by, so that's a perforation. Okay. We also have, for example, we drill our well and some part gets invaded by drilling mud. Okay. So the flow here will have certain characteristics, but when it flows through the mud might damage the formation and it will be impaired the flow. So that's mud damage. Okay. You also have, for example, if you sometimes you use in the wellbore, you put some gravel pack. Okay, you put some sand of different size, just to avoid wellbore collapse, and it will act like a filter. Okay, to filter the particles from the formation. So that's called gravel pack. And that the flow through the gravel pack is also captured by the IPR. Okay, sometimes you use you make some slots. Okay, you use some screens. For example, here you have the formation, and then the fluid has to go through these small openings that they are causing some restriction, and that might be also included. Remember that the PWF is here, so that includes also those losses in that screen. Then one more thing that can use for horizontal wellbore, for horizontal the IPR captures sometimes flow in the wellbore. For example, we have our horizontal section like that, and we have flow all along the wellbore. Sometimes we put our PWF here, and that has both flow through the formation and flow inside the pipe. Okay, so that's also might be captured by the IPR. What else do we have? Or I forgot. Also, we have the well radius, the wellbore radius. We have the formation thickness. Okay, if we have our well, the thickness, the H, is also included in the IPR or affects the IPR. Then we have the volume average pressure of the drainage area, and that's what we call the reservoir pressure. And then we have a high velocity effect. Okay, that's non-Darcy effect. That sometimes we don't have just that equation, we just don't have that behavior, but sometimes we have that we have something like that. That depends AB plus CV squared. Okay, that no longer is just Darcy that is linear with velocity, but is to the velocity squared. You have some high velocity component. So that's also captured by the IPR. And the convergence effect of the flow towards the wellbore. If you see from the top again, I have my well and I have my drainage area. So every time you have to cross kind of a different area that is bigger initially and it becomes smaller and smaller and smaller. So that geometrical effect, when you have this convergence of the flow, every time you have the same flow that has to circulate through a smaller and smaller and smaller area. So that part is also captured by the IPR. Okay, more or less clear?
Can you capture the relationship between vertical and horizontal permeability if you have a horizontal well?
From vertical? Yeah, but that's in the permeability. Okay. Permeability of the formation, KV, KH, or we call it K set, KY, and KX. Okay. The variation in each direction of the permeability. So you see all of that. It's almost like a reservoir simulator, but for the very close region to the wellbore, and applies to stabilized flow. When the transient, the short-term transient has disappeared and the pressure change has reached the bound. Now there are two methods to calculate IPR, to estimate IPR. And one of them is well test. Just like I mentioned before, you run a test at different wellhead pressures, bottom hole pressures with time. You put a value, then you change another value, and you have to wait. And it's better. Remember, if it's a linear, if it's a straight curve, you need just 1 point, right? But if you have a curve, then it will be nice to have many points to try to tune, okay, the CNN, for example. And the rate is going to, the first is constant, and then change, then it will be constant more or less, change, constant more or less, and change, constant more or less. So those are all the points, and you at the end plot those points, PWF versus Q, and plot those points. Okay, if it's a straight line, you really were wasting time. You need just 1 point. If it's a curve, then it's good to have many points, because then you can then it's good to have many points, because you can tune your equation better. But remember this procedure, we don't want to put the well in test usually because it's very expensive. But it's the only way to know our well, how our well is producing. So there is all the time a fight between the production engineer and the manager, Let's put the production engineer with a helmet. Say I need to know more information, better information about my well, and I need so many points. The manager is going to say, no, you just need 1, or you don't need any point. So there is force and back and trying to justify why you need to test the well. Remember, test the well, it's maybe simple operation on land. You don't have to move this portable separator and put the well to test offshore. We have to send it to we have to reroute it and send it to the test. So it's a big thing. And there are some equations typically used are the linear IPR, and that's applicable for undersaturated oil, plus water. And the equation, we have seen it just before. Sometimes it's made in base of liquid. That will be Q oil plus Q water. And is equal to a factor called J times PR minus PWF. So if you have PR, and you have 1 point, you can calculate how much is your J. Then you have, for gas, the back pressure equation that we have already discussed. Equation, that's for gas, or it could be used also for saturated oil. And you remember the shape is Q equal to C PR squared minus PWF squared to the power of n. Yep. Then you can also use the Vogel equation, and that's typically for saturated oil. And the equation is something like QO max. That's QO at PWF equal to 1 bar, okay, 1 atmosphere, or what we call absolute open flow potential, or absolute open flow. Times 1 minus 0.2 PWF over PR minus 0.8 PWF over PR squared. Okay, in that case, that equation, you just have to tune the QO max. If you have, and maybe we will make an exercise, or you will get an exercise on that. Okay, if you have your collection of points, you have to tune that value here. That's the absolute open flow until the line passes through all of the points. And actually, that's the exercise you have. Okay, the fourth exercise is using that equation. And then another equation that we use is the composite IPR, and that's for reservoirs that are saturated and undersaturated oil. Okay, and that works in the following way. Q oil, PWF, for example. If you are PWF is below the bubble point, okay, bubble point pressure, you use the linear IPR. Then if it's lower than that pressure, you use Vogel. Okay, for values, for pressure values below that. So that's for undersaturated reservoirs, when you can have production above and below the bubble point. So that's one way to calculate IPR, and I can use any equation. But remember, if with time the IPR will change, okay? So I have to run tests at every point in time that I want to analyze, okay? And that costs money. Remember, at another time, with depletion or with time.
Mira,
yes?
should it be PWF higher than?
Yep.
PB?
Thank you. And here is for PWF less than PB. That's correct. With time, the IPR changes. And really, with these empirical models, we cannot know exactly how they're going to change. Okay? So we have to run, it is necessary to run a well test again to find out exactly how the IPR changes with depletion. Okay? And that's a very expensive procedure. So there is another approach to estimate IPR. IPR can be also estimated analytically. Okay. What is the advantage of having an analytical expression for IPR? It's an equation, okay, that comes from some physical principles. The advantage is that if we have a model, okay, a reservoir model or a tank model, we can predict how the properties will change with time. And then we can take those properties and populate my IPR and calculate exactly how the IPR will look like with time. So we don't have to run a well test. And that's especially useful for field design. Okay? And the analytical expressions are usually derived for the expressions are derived from, and don't be scared, okay, we have this ugly equation. That's for radial flow and vertical wellbore. Okay. From differential equations, okay, that they have the conservation of mass and the conservation and momentum. Conservation of mass and momentum. In this case, it's just conservation of mass, sorry. And apply to the particular geometry. Okay, if it's a radial well, vertical well, I apply to that particular coordinate. If it's a horizontal well, then I also I customize the equation for every for each situation, okay, for each well geometry. And at the end, I end up, for example, with equations, some examples for I think this, the first one we have here is gas. For dry gas, Qg equal to KH T standard conditions over T reservoir P standard conditions, ln of RE over RW minus 3/4 plus S integral PWF PR of 2 pressure over mu G set dP. And for oil, just to give you some examples, okay, but there are many expressions. You will see when we go to Prosper, there are many equations, many analytical equations derived exactly from the same. You go from the differential equations, you customize the equation for each situation, and you solve it. And you make some assumptions to solve it. Okay, for oil, for example, it's have you seen these equations before? Okay, and if we, for example, for undersaturated oil, for example, K you have just oil, so you have KRO is just K relative permeability. You have only oil flowing through the system. So K over mu O BO is constant with pressure, so it can be taken out of the integral. So at the end, that gives you QO 2 pi KH ln RE RW minus 3/4 plus S, and K over mu O BO PR minus PWF. And all of that is what we already knew from before, the linear, the PI, okay? And you can calculate, but that shouldn't change because that one is independent with pressure. K, actually that K should be, that is 1 actually, okay? It's not equal to, but it's equal to 1. Because K is the permeability of the oil phase divided by the absolute permeability. So that should be 1.
Water is aimable. You are neglecting water.
Sorry?
You are neglecting water.
Yeah, you're neglecting. Well, you assume it's well, it's in this case if or something less than 1 if you have connate water. Okay, but it's constant because the saturation is all the time constant in the reservoir. KRO, as I told you before, is a function of oil saturation, and oil saturation is constant. So KRO is just a value, okay? Less than 1. Okay? But it's constant. But what I'm saying is that all of that is constant, so that's called J, and you can estimate analytically, or you can go and measure, and then but it's exactly the same thing. In that case, it won't change with depletion. You do it for gas, for example, that number will change with pressure, and that will tell you how the C and the N will change with depletion. Okay? So we have two approaches. One, this is very uncertain, is based on equations, and we should all the time check it with well test. Okay? But the nice thing is that if we have those values, how the pressure will change with time, we can calculate how the IPR will change with time. And that's what you're going to make on the exercise. On the other hand, we can have all of these kind of empirical equations, but then we have to tune. We have to have values in every point in time to tune them. Okay? Any question? No? More or less clear? Yes? Okay, so just to see what we saw today, it's equilibrium. Okay, I can take out the component or keep the component. It's the same, it's equivalent. It depends on your preference. But I tell you, if for design, if you don't have the equipment, it's better to remove the component. But if you have the equipment, then you can leave it, but then usually you have to run this solving process. Okay, people call it optimization. Then the next thing we mentioned was multiphase flow. The curve looks very different, decreasing and increasing, and there is some physical reason for that, but usually we keep that information on tables. We pre-compute. Running these models is expensive, so we pre-compute, keep them on tables, and then we have to interpolate on the tables. And we have to take the potential variations of GOR, water cut, wellhead pressure that might happen, and then we talk a bit about IPR, just showing you what the IPR contains. It's really just a near wellbore simulator, basically, assuming stabilized flow, pseudo steady state. And we can find it two ways. One, well test data, we tune to an equation, but then we don't know how to predict the change with time. Or we can have an analytical equation, very nice, very complicated, but usually not so accurate, and we have to find how the properties change with pressure. Okay, so we close the session. See you on Thursday.